It is my real pleasure to welcome Mario Spera from SISSA in Trieste. Mario had his PhD at Sapienza in Rome. Then he moved in Padova for a postdoc, and in there he started really working on stellar evolution in binaries and this connected to LIGO Virgo sources. We all know this is a very timely topic. After that, he got a postdoc in Innsbruck, and then he got a Marie Curie fellowship that he spent in Northwestern University in combination with Padova University. And very recently, he got an assistant professor position in SISSA in Trieste. And today he's going to tell us about the formation and evolution of merging compact object binaries. So welcome, Mario, and you can start.
Thank you so much, and Elisa, for the presentation, and good morning, everyone. And thank you so much for inviting me to give this seminar. And I hope everyone is doing great despite the unusual circumstances we have to face at the moment. So I sincerely hope everything will be soon back to normality for all of us. So in this talk, I will discuss some of the main astrophysical ingredients that can give us some insights on the formation pathways of some gravitational wave sources, including the recent events GW190814 and GW190521. That is, the LIGO Virgo event with the most asymmetric masses and the event with the heaviest black holes, respectively. So my plan is to first discuss the basics ingredients that we need to understand if we want to study merging compact object binaries, like single and binary stellar evolution processes. Then I will also comment on their effect on the mass spectrum of compact objects. And I will also briefly discuss the effect of stellar dynamics. Finally, I will discuss the connection of these processes with the formation of gravitational wave sources, with a specific focus on the events that I just mentioned, like 190814 and 190521. So let me start with a little bit of background information. So first of all, my research interests, which are basically let's say, my main research interest is the study of the interplay of stellar evolution and stellar dynamics in different stellar environments. Of course, I want to study this interplay not only from the theoretical point of view, but I also like the computational point of view of this kind of interplay. I also like to basically develop the algorithms behind stellar evolution and dynamics. The main aim of my research is to investigate this interplay between stellar evolution and stellar dynamics, so that I can give possibly an astrophysical interpretation to present and forthcoming LIGO Virgo detections. And I would like to do that because we now have tens of LIGO Virgo gravitational wave detections for merging compact objects. But from the theoretical point of view, we still don't know much about merging compact object binaries. So this cartoon is just to remind you where we are in terms of gravitational wave detections. In blue, in this cartoon, you find black holes from LIGO Virgo. In purple, black holes discovered thanks to electromagnetic observations, mainly from the observation of galactic X-ray binaries. In yellow, you can see the known neutron stars, and in orange, the binary neutron star from LIGO Virgo. And here on the y-axis, you have the mass in solar masses. So the event highlighted up here is GW190521, and this event here, this very weird event, is GW190814. Well, now, of course, we are now sure that binary black holes exist, and we know that they can merge within a Hubble time. But more importantly, we know that massive stellar black holes exist, possibly in the range of intermediate mass black holes. And so this triggers some astrophysical questions. The main questions are how such heavy black holes form and how they merge within a Hubble time. Actually, we do not even know if the black holes detected by LIGO Virgo, for example, formed independently from each other and then they met at some point in their life and they merge, or if the progenitor stars of these compact objects were bound since the beginning of their life, they evolved in complete isolation. We cannot actually distinguish between these two formation scenarios. So if we want to answer these questions, we need to study, first of all, the black hole mass spectrum in general, the compact object mass spectrum that we obtain from a population of isolated stars. And then we need to also study the physical processes, for example, that take place when two stars are members of a binary system. And we also need to take into account that actually most stars do not form in isolation, but in aggregates, in associations, in dense stellar environments, in clusters. So, and these are environments where dynamical interactions can play a very important, a crucial role. So, this cartoon is just to remind us all that if we want to have a crystal clear view on how black holes and compact objects in general form, evolve, and possibly merge together, we need to understand stellar evolution processes for both single and binary stars. And we need to constrain also the supernova explosion mechanisms, which is very complex and uncertain. And then, last but not least, we also need to take into account stellar dynamics, because as I mentioned, stars do not form in isolation, but in aggregates and in dense stellar environments. Unfortunately, I do not have time in this talk for an in-depth discussion on each of these aspects, but I can show you how crucial all of them are for the formation and evolution of merging compact object binaries. Let's start from the evolution of single stars. Okay, specifically, we know that stellar winds play a major role to understand the compact object mass spectrum. We know that stars can lose a significant amount of their initial mass through stellar winds during their life. For example, if we look at this wonderful picture taken by the Hubble Space Telescope of this star, which is WR124 in the Sagitta constellation, you can see that basically the surrounding nebula here is the mass lost by the star through stellar winds. So this star basically at present is a 10 solar mass star. It's a 10 solar mass object, but its initial mass had to be something like very close to 30 solar masses. So the mass loss through stellar winds can be huge, and we know that this depends crucially on the mass of the star and its metallicity. Specifically, metal-rich stars lose significantly more mass than metal-poor stars, and massive stars lose more mass than low-mass stars. So this is the first ingredient. And we also know that the final fate of massive stars can be quite dramatic and uncertain. They end their life, we know that they end their life with a big explosion, with a big boom, with a supernova explosion, leaving a compact remnant, which could be, depending on the initial mass of the star, a neutron star or a black hole. So the supernova explosion mechanism, that's the main issue. The main issue is that the supernova explosion mechanism is very complex and uncertain. The mass of the compact remnant actually depends on many things, including the final mass of the progenitor star, the mass just before the supernova explosion, which in turn depends on how much mass the star has lost during its life through stellar winds, for example. Moreover, the compactness of the star just before the supernova explosion can also play a crucial role. Also, the rapidity of the explosion itself and the amount of mass that may fall back onto the protocompact objects. All these things may play an important role. Though theoretical models tend to agree that there should be a threshold value for the final mass of the star, above which the star itself does not explode as a supernova, and it directly collapses into a massive black hole. So this is the phenomenon of the failed supernova, also known as direct collapse. On our side, so one of my main research topics and what we did in the last years was to try to put together up-to-date prescriptions of all these ingredients for the evolution of single stars to obtain an up-to-date compact object mass spectrum that we could use to give an astrophysical interpretation to, for example, the heavy black holes detected for the first time through gravitational wave, through the LIGO-Virgo gravitational wave interferometers. So we developed basically from scratch a new tool, a new population synthesis code that could bridge the gap between the outdated population synthesis codes and the recent advances in stellar astrophysics. So this is the 7 code. This is basically the code we use right now to study compact objects. It's a population synthesis code that is a code basically that can evolve a population of either single or binary stars from the beginning of their life until they turn into compact remnants. Of course, I won't bother you with the details of the 7 code, I just want to mention that in 7, I included basically up-to-date prescriptions of stellar evolution and stellar winds, and also several up-to-date prescriptions for supernova explosion mechanism. To evolve stars, 7 reads a set of lookup tables that contain basically pre-evolved stellar evolution tracks that are interpolated by 7 on the fly. So this means that basically 7 is very versatile, because if one wants to change stellar evolution prescriptions, for example, if one wants to test or compare the results he obtains using different stellar evolution models, it can do that because it can just generate a new set of lookup tables without touching or changing the code inside. But let me show you what we obtained with this code. This is basically what happens when we included all these up-to-date ingredients in the 7 code. So this plot shows you the mass of the compact remnant as a function of the initial mass of the star, and the curves correspond to different metallicities. As you can see, basically stars at low metallicity, for example, the purple curve up here, form heavier black holes than stars at higher metallicity down here, like the red or the brown curve down here. But probably the weird aspect of this plot is that it is not always true that heavier stars form heavier black holes than lighter stars. Let's focus on the purple curve right here. So you see that basically the curve grows as the initial mass of the star grows, but at some point it shows an inverse trend, and actually it goes even to 0 for stars with masses larger than, say, 110 solar masses. So the curve, of course, going to 0 means that stars with mass larger than 110 solar masses basically leave no remnants behind. Though you can see that the purple curve goes up again here as the initial mass of the star is above, say, 230 solar masses. So this may be considered kind of weird aspects. And the main effect of these weird curves is that they basically create a gap in the black hole mass spectrum. That is a mass range between, say, 60 and 120 solar masses, where stellar black holes cannot form, accordingly to up-to-date theoretical models for the evolution of single stars. Why the curves are so weird? So what happens to massive stars? So the curves are weird at first sight, and why, for example, GW190521 is referred to as a special event. So the gap is caused by pulsational perinstability and perinstability supernovae. Perinstability supernovae are quite different from the, let's call them usual or standard core collapse supernovae. Massive stars at the end of carbon burning in their cores, just before oxygen ignition, undergo the phenomenon of pair productions in their cores, which means that photons are converted into matter. So this basically softens the equation of state and reduces radiation pressure. So basically, as a consequence, the star collapses and oxygen is ignited explosively. So the star becomes unstable. Now, stars with helium cores with masses between, let's say, 32 and 64 solar masses start pulsating. And these pulses basically significantly increase mass loss. In contrast, and this is the so-called pulsational peri-instability supernova. In contrast, if stars with a helium core masses larger than, say, 64 solar masses undergo only one single violent pulse that completely destroys the star with no remnant mass left behind. This is the so-called pair instability supernova. So this explains why at some point the mass spectrum curves showed an inverse trend. Massive stars may enter at some point in their life the pair instability phase, lose a significant amount of mass, and forming so lighter black holes, or even no remnants at all. It is worth noting that very hot cores of very massive stars, I'm talking about very exotic objects like stars with masses larger than, say, 200 solar masses, might be able to overcome the pair instability phase because the conditions basically in their cores are not favorable anymore for pair production. And theoretical models predict that stars start to collapse again into very massive black holes, possibly in the domain of intermediate mass black holes. Surprisingly, the upper mass gap is not the only gap that theoretical models, and in this case observations, predict in the compact object mass spectrum from single stellar evolution models. We do have also the so-called lower mass gap, which is a gap that is supposed to exist for compact objects with masses between, say, 2.5 and 5 solar masses. The presence of the lower mass gap was originally suggested by electromagnetic observations of neutron stars and galactic black holes, shown on the left and on the right panel, respectively. Most black holes here within the uncertainties, of course, have masses above, say, 5 solar masses, especially if we exclude the blue points here, which are the most uncertain. And in contrast, all neutron stars have masses below, say, 2 solar masses, at least those with more constrained measurements, like this one up here. Possibly, of course, there are a few exceptions in both the populations, like this, for example, putative supermassive neutron star. And actually, this plot was updated to 2016, but we now have a few more candidates for supermassive neutron stars with masses larger than 2 solar masses. But at that time, this was enough to suggest the possibility of the existence of a lower mass gap. Anyway, whether the lower mass gap is caused by some physics we do not really understand, or is just caused by selection biases and or uncertainties in the X-ray observations, is still under debate. From the theoretical point of view, we do have in the literature some very simplified supernova explosion models that reproduce the lower mass gap. So one of these models is the so-called rapid supernova explosion model. This is called rapid because the instabilities that trigger the supernova explosion develop very rapidly, talking about order of milliseconds. And the rapid model is very sensitive to the internal structure of stellar cores. And star with zero age main sequence masses between, say, 22 and 27 solar masses develop very compact core structures that make the supernova engine to fail. So this means basically that these stars in this range basically collapses to form quite massive black holes. And this is what you see here in the left-hand plot, which shows the compact remnant mass as a function of the initial mass of the star when the rapid supernova explosion is adopted. The rapid model creates a peak here of massive black holes, and of course this creates a gap down here. There are also some more sophisticated supernova explosion models that tend to confirm this feature of simplified supernova explosion models, like this one. So you see in the right-hand plot here, you see in red, this is the so-called compactness parameter of the star. So this is a measure of how much a star, actually a stellar core, is compact just before the supernova explosion. So this is the compactness as a function of the initial mass of the star. And you see basically in red, the stars that undergo a successful supernova explosion, and in gray, the stars that undergo a failed supernova. And you see that basically ZAM's zero-age main sequence initial masses between 22, say, and 25 solar masses tend to not explode as supernova because their cores are significantly more compact. But of course, not all the supernova explosion models predict the existence of the lower mass gap. The so-called, there is, for example, another supernova explosion model, simplified supernova explosion model, which is called the delayed supernova explosion model, that, for example, does not predict the mass gap. It basically, if we would have used the delayed supernova explosion model in this plot, we would have obtained basically a monotonic trend here. No jumps, so no mass gap. But this was just to show you that indeed the presence of the lower mass gap is very debated from both the observational and theoretical side. Where do we stand in terms of gravitational wave detections with respect to the two mass gaps? That's a $1 billion question, basically, because, well, you see in this plot, basically this plot comes from the LIGO Virgo population paper for the first two observing runs, O1 and O2. And this was basically the scenario updated to September 2019, yeah, about 1 year ago, okay? So it shows on the left-hand panel the masses of the detected gravitational wave events from the lightest to the heaviest black hole binary, including the binary neutron star down here. And the black squares represent the black hole masses, while in red, the red triangles show the mass of the merger products. On the right panel, you have these plots shows the theoretical models obtained using our own 7 code with the gray horizontal bands that represent the mass gap areas. The upper mass gap up here and the lower mass gap down here. And as you see, these models, these theoretical models here have this bump here. So it means that they use the rapid supernova explosion model. So the supernova explosion model that enforces the presence of the lower mass gap. So you see that all the black holes detected by LIGO Virgo were at that time, so 1 year ago, all of them consistently outside the mass gaps, if we exclude, of course, the merger products. And everything could have been, in principle, not very hard to explain by means of just up-to-date stellar evolution models. But as usual, you know that things went out to be slightly more complicated, but exciting. What you can see here is a more updated version of the plot, which includes the two curious cases of GW190814 and GW190521, down here and up here, respectively. These events are marked in red here in this plot. So both these events, even if for very different reasons, challenge our current theoretical understanding on how stellar black holes form and evolve. And both these events open up new investigation scenarios. The primary component of GW190521 here falls right into the upper mass gap. And the merger product falls basically right into the domain of intermediate mass black holes. So this is finally the first confirmation that such fascinating objects exist. On the other hand, the secondary of GW190814 is an object of basically 2.7 solar masses, and besides the uncertainties we can have on its nature, that is, we think it's a black hole, but we cannot totally exclude that it's a neutron star, this mysterious object falls right into the predicted lower mass gap. So therefore, this specific event might challenge all the astrophysical models that predict the existence of the lower mass gap. So we have got actually a very robust measurement of the mass of the secondary of GW190814. And so this challenges even more the presence of the lower mass gap. And furthermore, we know from the theoretical point of view that the very asymmetric mass ratio of GW190814 challenges all current astrophysical models, because the latter in general tend to favor the merger of compact objects with more similar masses, with less extreme mass ratios. From the astrophysical point of view, the question now is, can we form compact objects in these mass gaps? And so, can we explain GW190814 and 190521? What are the possible formation pathways of such weird compact objects? So far, as also in the right-hand panel of this plot right here, I showed you theoretical models only for single isolated stars. But all these gravitational wave events, of course, involved the merger of two objects. So the first natural thing to show you is what happens to theoretical models, these curves, when we take into account binary stars. Well, binary stars significantly complicate the theoretical scenario. we know that two stars, members of a binary system, when they are member of a binary system, basically we know that in this case a lot of complex physical processes may take place. For instance, one star may fill its Roche lobe radius and start transferring mass to the companion star, like in this cartoon here. And this process may proceed even on a very short time scale. So even numerically, this is very difficult to model and very uncertain. And we also, another thing which is difficult to constrain is the amount of mass which is transferred to the secondary object during this phase. But these, of course, may be crucial to understand the black hole mass spectrum, and possibly these may help astrophysical models to form objects in the mass gaps. Or even that could be an even more dramatic scenario. These two stars, or the star and one compact object, may even merge during their life as a binary system. So they may create just one single object, which is the merger product of the two. So at the end, it is legit to ask ourselves, can binary stellar evolution processes favor the formation of compact objects in the mass gaps? We, during the last year, we worked hard on this point, and we performed a major upgrade of the 7 code, where we included up-to-date binary stellar evolution prescriptions, so that we can also take into account mass transfer, common envelope, tidal dissipation, supernova kicks, and all these very complex and uncertain ingredients. And we basically use the 7 code to investigate the effects of binary evolution processes on the compact object mass spectrum. At this point, I would need a separate talk to describe all these binary evolution processes in details, or in the detail they deserve. But in contrast, in this talk, I would like to keep my focus on the link between binary stars and the mass gaps. Especially, I will focus more on the upper mass gaps. I'm pretty sure I won't have time to discuss also the lower mass gap in detail. So let me show you what we obtained for the black hole mass spectrum from binary stars. So starting from binary system, of course, we have in general 3 possible evolutionary scenarios for example, for black holes, or for binary black holes. If the 2 stars do not merge during their life, and if they are massive enough, they end up forming a black hole binary, which could be large, so it does not merge within a Hubble time through gravitational wave radiation. Or the progenitor star could form a tight black hole binary system, a possible loud gravitational wave source. And there is also another scenario. 2 stars can merge during their life, and then they might form just one single black hole. So these plots show you the mass distribution of black hole masses from all our simulated binary systems. And the different curves represent the different scenarios I just described. So specifically, the red curve refers to all the black holes that are members of black hole binaries, and the black curve shows the single black holes that come from gravitational wave merger. The green curve is the curve that shows you the single black holes that come from gravitational wave mergers, and the black curve shows all the single black holes, not necessarily coming from a previous merger, okay? The gray area of these plots, the left hand is at solar metallicity, high metallicity, basically, and the right hand plot is at low metallicity. This gray area here show what we obtain for the black hole mass spectrum if we use only isolated single stars. So these plots show a very interesting feature, both at high metallicity and at low metallicity. They show that basically, in spite of pairing instability supernova, it is possible to form massive but single black holes that fall right into the upper mass gap of the black hole mass spectrum, the gap predicted by pairing instability. So I'm looking at the black curve here, at this tail here, and this tail here. We can form single black holes with specifically with mass up to 60 solar masses at solar metallicity and up to 140 solar masses at low metallicity. These objects are single objects, isolated, and they are, of course, quite rare. We form, in this case, for example, we form one of such heavy black holes every 10 to the 3 other black holes. But they are there, they are here actually, and they are not insignificant. How these black holes in the upper mass gap can form? What's their formation pathway? So, well, most of them come from the merger of an evolved star with a main sequence star. I would like to stress that such heavy black holes do not come from previous mergers. So from the previous merger of two lighter black holes. So these black holes are referred to as a first generation black holes, not second generation black holes. This is an important detail. I will explain you why. In this scenario that we presented in one of our recent papers, we have a main sequence star and mergers with an evolved star. And during this phase, the evolved star may acquire quite a lot of hydrogen from the main sequence star. So after the merger, we might end up with an evolved star with an overmassive hydrogen envelope. Though the star is already at an advanced stage of its life, and likely it does not have time to relax, reprocess, and burn in its core all the newly acquired hydrogen. So basically, the central core does not grow significantly and stays below the threshold for the pairing stability, and the star ends its life collapsing into a massive black hole whose mass includes also the excess of hydrogen acquired from the main sequence star. Thus, in this case, the helium core basically must stay below, say, 30 solar masses, and the hydrogen acquired above here is on the envelope of the evolved star should be likely larger than 15 solar masses. This avoids pairing instability and might possibly form a black hole in the upper mass gap. Of course, there are some caveats to mention in this scenario. We do not know, for example, what's the fraction of hydrogen acquired by the evolved star. It could be all of it, or even only a few percent. And we do not know what's the hydrogen fraction that falls back onto the black hole during the direct collapse phase. So the only way we can constrain these parameters is with more gravitational wave detections of heavy black holes. So we certainly hope we will find more in the next years. Actually, there is another caveat we should mention in this scenario. And the issue here is that this scenario alone cannot really explain the detection of gravitational wave sources with the black holes in the mass gap. Why? Because the heavy black hole that forms through this scenario is isolated. It's a single black hole. It does not have any chance to meet another black hole and to merge with it in a Hubble time, because simply the companion black hole is not there. We just simulated the evolution of binary stars. These binary stars become one single object, and this black hole is lost in the universe alone. So, but we still miss one possibly crucial ingredient in this scenario, which is stellar dynamics. Two stars or two compact objects do not need to be bound since the beginning of their life to become loud gravitational wave sources. Two black holes, for example, might become bound after one or more gravitational encounters. And gravitational encounters, we know that these encounters are quite common in star clusters, for example, in dense stellar environments. And we know that it's quite common to find stars in star clusters because stars actually form in dense environment, in aggregates, and not just isolated. So, like, for example, just to give you an example, like the beautiful picture here, which is a young star cluster, that's a picture taken by HST. That's the R136 cluster in the Large Magellanic Cloud. So it's an aggregate, it's an ensemble, dense ensemble of stars, young stars. So stellar dynamics might play a crucial role to understand the origin of merging compact object binaries. How binary black holes may form in dynamically active environments? Well, most of them form through a dynamical exchange of membership. That's how we call it. Suppose, for example, you have a black hole star binary in a star cluster. And dynamical exchange happens basically when, for example, another black hole dynamically interact with the binary and replace the star as a member of the binary system. This is, of course, not an exotic scenario, because for black holes, we know that black holes are particularly efficient in acquiring companions via dynamical exchanges because they are among the most massive objects you can find in a star cluster. And exchanges tend to favor the formation of more massive binaries with smaller semi-major axes, simply because the final configuration represents a lower energy state, so a more stable or energetically convenient configuration. So, and we showed that more than actually 90% of binary black holes form via dynamical exchanges in star clusters. So, therefore, in principle, if the black hole formed from the merger of a main sequence star and with an evolved star is also a member of a dense stellar environment, the heavy black hole likely acquires a companion star or directly a companion black hole, like in this cartoon here, and maybe after a three-body encounter, and they can form a hard binary that can merge within a Hubble time, and so becoming a loud and detectable source of gravitational waves, like GW190521. We actually investigated this scenario. From our side, what we are trying to investigate is the role of young dense star clusters in the formation of merging compact object binaries and in the formation of black holes in the upper mass gap. Specifically, in this paper, we investigate the possible signatures of stellar dynamics on merging black holes in young dense star clusters. This is the first author of this paper is Ugo Niccolò Di Carlo, a PhD student from the Michela Mapelli's research group at the University of Padova. So I won't give you the details of all the simulations, but we basically combined state-of-the-art N-body, gravitational N-body simulations with state-of-the-art stellar evolution prescriptions, and we simulated, we performed a statistical study of merging black holes on a sample of more than 4,000 young star clusters. We actually, let me show you, first of all, let me show you what we obtained from these simulations. This figure shows for all the merging binary black holes, the mass of the less massive remnant as a function of the mass of the more massive remnant for binary black holes, for merging binary black holes that we have in our simulations. The blue points show the merging dynamically formed binary black holes, while the orange points are, and the density map here, show the merging binary black holes that come from isolated binaries. No dynamics. And here, the red stars are the LIGO Virgo detections updated at 1 year ago, basically in 2000. That was the situation in 2019. Interestingly, you can find that basically this event up here is matched only by merging dynamically formed binaries. So this means that, that basically, if we would have included GW190521 in this plot, which is basically up here, around here, these would have fall in a region where only dynamically formed binary black holes were present, so the blue points. Of course, we also, and specifically, we also have a few merging binary black holes with at least one of the two black holes in the upper mass gap. And these black holes form through a dynamical process, and these are first generation black hole. These are not coming from a previous merger of two lighter black holes, but these come from the scenario that I just described for the merger, from the merger of an evolved star with a main sequence star that form a massive heavy black hole. Of course, what's the main issue with these simulations? The main issue is that we need more simulation. We need more simulation, but the problem is that these simulations are extremely expensive and time-consuming from the computational point of view. I mean, even if we use graphics processing units to evolve these systems, and we simulate relatively small clusters with containing up to, say, 15,000 or 20,000 stars, these simulations are a nightmare, especially because we need to resolve all the motions of tight binary systems. So the time step from these simulations become extremely small. And the simulations are very, very, very slow. But of course, we need more because we need to populate, and we will populate also this area with more statistics. And this is certainly one crucial point, especially for the next years. So obviously, there are several other possible channels that can form black holes in the upper mass gap and explain the formation of exotic events like GW190521. I already mentioned the collapse of stars with an oversized hydrogen envelope and second generation black holes. But very heavy black holes can form also from accretion in disks of gas around active galactic nuclei, or maybe, and I say maybe, the uncertainties on the lower edge of the upper mass gap are such that the primary black hole of GW190521 is not in the mass gap, and is actually outside the mass gap. So maybe GW190521 might not be exotic at all, or at least the primary component of GW190521 may be outside the upper mass gap. Or maybe there are even other still unexplored scenarios. I don't have time to discuss the other things, but I will leave you with some take-home messages. I showed you why 190814 and 190521 represent actually special, why they are called special events. And I just wanted to give you a brief overview of the ingredients we are working on to provide an astrophysical interpretation to not just these two special events, but also to other present and forthcoming gravitational wave sources. I showed you that basically up-to-date models for the compact object mass spectrum from those singular binary stars are crucial, of course, if we want to understand merging compact object binaries. And I showed you where the latest two gravitational wave events stand with respect to the mass gaps predicted by theoretical models. And I also showed you, I wanted to show and to present a possible alternative scenario to form black holes in the upper mass gap, which can possibly explain the formation of GW190521-like systems. So can we say something about the origin of 190814 and 190521? Well, we do not have a conclusive answer to this question, but we've got some hints, as I showed you. 190814 might challenge all the models that predict, for example, the existence of the lower mass gap. And 190521 is also very difficult to form from non-dynamical scenarios, assuming that the primary black hole of 190821 falls in the upper mass gap. So future gravitational wave events will definitely help us to better constrain astrophysical models and to maybe give soon a conclusive evidence for the origin of a gravitational wave event. And thank you so much. I finished here.
Thank you, Mario. Thank you very much for the very nice talk. And so now we take questions from Mario. I saw there is already a question on the Zoom, so I will read it from Presenji Saha. The mass estimates assume standard siren binaries. Can LIGO rule out collisions of two black holes in three-body systems?
That's a very, very good question. Can you hear me?
Yes.
Okay, that's a very, very good good question. No, we cannot at present. Actually, we cannot rule out anything about three-body collisions, or because actually we are at one step before that scenario. We cannot even rule out. We cannot even distinguish between different scenarios in terms of isolated binaries and dynamical. So including also three-body encounters and collisions in three-body systems is even more hard to constrain. So at present, actually, we cannot rule out triples, basically, and their role. So that's still under investigation. Also because we are not sure, for example, when you simulate one young dense star clusters, you do form triple systems on the fly, but they are very difficult to follow from the numerical point of view. And you can basically follow their evolution only for when you simulate relatively small clusters, because otherwise everything becomes computationally prohibitive. So, and we don't even know if some triples may be there since the beginning of a cluster life. In principle, that could also be true. So definitely triples are a matter of investigation. It's a very also interesting scenario, but at present we cannot rule out anything.
Okay, thank you very much for the answer. So I just want to, sorry for not saying it before, people on Zoom, if they want to ask questions, can raise their hands so that I can, you can then ask the question directly. And in the meantime, there is Jacob here who has a question. Maybe you can come closer so that everyone can hear you.
Can you understand me?
Yeah, sure. Hi.
Hi, thank you very much for the interesting talk. I have two questions, actually. The first one is somewhat related to the previous one. So it sounds to me that in the mechanism you propose to produce black holes in the upper gap from the stellar collision of two stars, it seems to me that it is very easy to have a merger if you start from an initial stellar quadrupole system in the field, right? Where these two are the first two stars. Then you have a tertiary black hole, or a star at first, which evolves to a black hole, and then a fourth object, which basically promotes then the merger via a Lidov-Kozai oscillation. Have you considered, I mean, you know, there are some papers discussing that, and the statistics of quadruples or multiple systems for heavy stars is actually quite good. So it's very reasonable to assume that you have such multiple systems. And maybe I have another short question.
Sure.
How well is the assumption justified that in the initial conditions you use for the population synthesis studies, that for example, the semi-major axis and the eccentricity, how well is it justified that this is independent of the metallicity you use? Is there any reason to believe that this varies from metallicity to metallicity?
Okay, these are very, very good questions, and thank you for asking these questions. So, as the first question about quadruple systems, yes, quadruples can actually trigger this scenario, basically. The main issue with quadruple systems is that they are very difficult to track in dense stellar environments, and in isolation, actually, it's even more difficult because it's difficult to basically study at that level the interplay between dynamics and stellar evolution. For example, there are some papers and some authors that show that mergers can happen in a quadruple system triggered by a Lidov-Kozai oscillation. The main issue with actually most of these papers, is that stellar evolution is ignored, basically, or considered only at order of magnitude. But stellar evolution actually, especially supernovae kicks and stellar winds, can actually significantly change the orbital configuration of a quadruple system. And so actually stellar winds, or even blow kicks when you have the supernova explosion and neutrino escapes, can even destroy a quadruple system. But this has never taken into account self-consistently, but just because we barely understand stellar evolution in binaries, you can imagine what happens when we talk about triples or quadruple systems. So that's of course a really exciting scenario, but that deserves definitely more investigation and as a self-consistent treatment of stellar evolution, which is still unfortunately missing. But that would be great to have such kind of tool that can combine such kind of dynamics and stellar evolution. So the other question is, yes, initial conditions for binary systems is another good point. Basically, what we use for they can in principle depend on metallicity. So what we use here is basically initial condition, and what other authors also generally use, but that's the only thing we can have right now. It's the initial condition taken from observations of the solar neighborhood. And so we take and sometimes we extrapolate the distribution of, say, major axis and even and periods, basically, and eccentricities. But that's definitely a good point. But at the moment, this is the only thing that we can have as initial condition of binary systems. So from observations of our solar neighborhood, and we are not sure even how these initial conditions can depend on metallicity, because they might in principle.
Thanks, Mario. So do we have any further question, either on Zoom or live here? So maybe I will ask a question myself. I was just curious, when you were talking about the two merging black holes, like the most massive ones that gave rise to like the first intermediate mass black hole, I was curious because my question is such kind of event easier to detect because of the large masses? Meaning that even if it's extremely rare, let's say, then we just have a way higher chances to detect it? Or is it something that just like it's not very biased observation wise, so we do have to expect that those events are pretty common even in the like physical universe, regardless of the biases?
So that's also a very good question. In principle, you do have let's say a relation between the masses of the object and the loud signal. So this can be in principle more easy to detect. But of course, the rates that have been estimated for such kind of events also take into account such kind of kind of correction of this effect. So we expect to observe some of these events also in the future detection, like a few percent of the total population of future gravitational wave detection should be composed of such heavy black holes. But this is also taken into account in the rate estimations.
Okay, thank you. So any other question? Yes, we have one live, so Kai can come here.
Hello, thanks for the talk. So I have
Hey,
a naive question. So in one plot at the end of your talk, you showed the two masses of the binary systems. Yeah. So I was just curious why they seem to be correlated in the simulations and in the observations as well.
Oh, you mean why they tend to be all of them on this line here on the bisection here?
Yeah, couldn't they be randomly distributed?
Is that the question?
Yeah.
Oh yeah, that's a very good question, and that's actually one of the reasons why GW190814, which is the event with the most asymmetric masses, which is basically down here, down here, challenges all astrophysical models. Basically, this, for example, for isolated binaries, and also dynamics actually, stars that the compact objects tend to have similar masses. Similar masses because in binary systems, even if you have a very unbalanced, very extreme mass ratio, all the stellar evolution processes in binaries like mass transfer, common envelope evolution tend to redistribute the material on these two stars. So basically, even if they start from here, which is possible because in our initial conditions of binary system, we do have initially large mass ratios, but then they basically tend to move up here in this plot. And that's the effect of binary stellar evolution processes. Even dynamics also in terms of binary black holes, for example, tend to favor dynamical pairing of heavy black holes, so with reasonably similar masses, because basically this is also a consequence of the fact that if black holes form in a cluster, the most massive black holes tend to concentrate all of them in the center of the cluster and then tend to pair up among themselves. So these naturally also tend to move binaries on these side of the plot. Of course, on this region here and this region here, well, this is just the less massive remnant with as a function of the heavier remnant. So all the points should be on this lower end triangle of the plot. So in this area here, you have black hole neutron star systems, and for these systems, basically the mass ratio is more can be more extreme. So that's why you have some kind of points down here. But in general, they tend to be on this area, and that's why also 190814 challenges all current astrophysical models, because it has a very extreme, let's say, extreme mass ratio.
Thank you.
Thank you, Mike.
Yep, no problem.
Okay, so do we have any further question? I also don't see any question online. So let's thank Mario again for the very nice talk. Thanks, Mario.
Thank you so much, everyone.
And okay, so Mario unfortunately couldn't come in person for obvious reasons, but of course, I think he's open to exchange ideas even later on, maybe.
Absolutely. I mean, feel free to contact me or even keep asking questions via email or whatever you prefer as a communication method. I mean, just let me know. I'll be happy to start a discussion with you all.
Thank you very much, Mario. Bye-bye, everybody.
Thank you so much. Thanks.